All right. Sorry for the delay, but as you all may or may not be aware, there was a scheduled power outage by AEP this weekend, so this thing was turned off, and as a result, it can take a little while for it to get fired up. So I've been wrestling with this for the past couple minutes. Sorry about that. The sign-in sheet's already going around. I don't really have much in the way of major announcements in here, really in steel design as well, other than the fact that in steel you have homework due on Wednesday. But other than that, there's really not a whole lot to talk about. Today what we're going to do is we're probably going to finish T-beams. If not, we might have just a sliver left over. And then we're going to get into doubly reinforced sections. There's a good chance we get into doubly reinforced today, so we will see. Let's just get right into it. So, oh my, it's freezing up on me. Okay. All right, so here's what I'll do is I'll just sort of recap the procedure for design for a T-beam. The big thing to keep in mind when you're designing a flange section, and this holds true whether or not you're dealing with a T-beam or an L-beam, it doesn't really matter. I'd argue for an L shape, you probably have more of a tendency for that to be a true T-beam just because the flange by its very nature is a lot shorter. So maybe that might be worth mentioning, but other than that, the procedure's the same. So remember, a T-beam design, we talked about this last time, how a T-beam is a known cross-section problem, because if you can design the beam independently and the slab independently and just combine them, you can determine the dimensions of the T-beam before you begin design. So in that world, when you're designing a T-beam, you can assume it's a known cross-section because you can figure out those dimensions before you get into the rigorous analysis. So, you know, we always want to compute the self-weight or the factored moments. Remember, the one sticking point with concrete beam design, and this is the same thing with steel beam design, but whenever you're designing a beam, you have to know the self-weight of the beam. And if it's an unknown cross-section, you don't know how heavy the beam is because you don't know what the beam looks like. But we don't have that problem here, so we don't have to assume the self-weight. Now, we do have to assume that phi equals 0.9, so that's something we would have to go check at the end. We also have to assume something about our case with analysis. In other words, are we dealing with a case of a rectangular T-beam, or are we dealing with a case of a true T-beam? Remember, the difference is we're talking about the shape of the stress block, not the shape of the beam, but the shape of the resulting stress block to achieve C equals T. So what we do in our analysis is we initially assume that we have a rectangular cross-section. So we assume that the neutral axis is in the flange, and then we make that assumption in order to determine the reinforcement ratio, the rho value. And then we take that rho value and we say, well, if we put that much reinforcement into the beam, how deep would our stress block be? And so, you know, we assume it's a rectangular cross-section or a rectangular T-beam, and then we immediately verify it in the next step. So if we have a rectangular T-beam, we just go AS equals rho BD and determine our steel. It's pretty straightforward. If not, if this assumption is invalid, then we skip forward a few steps and go to step 8. So this is what we did in our last example. We found that it was in fact a rectangular cross-section, and so area of steel is rho BD. Choose a reinforcement pattern and then analyze to verify that you meet ACI requirements and verify that phi mn is greater than or equal to mu. Again, trying to shoot for a 90% or higher efficiency. Now, if you have a true T-beam, remember, true T-beams, what we do is we split them up into the flange moment couple and then the web moment couple. We split the T-beam up into those two separate sections. And the reason why we do that is because the flange couple, if you look at all of the expressions relating to the area of steel, the compression equals tension, the moment capacity, none of that has anything to do with A. So it doesn't have anything to do with the steel that we would put in the section overall. So basically what we say is, okay, we split it up into a flange couple and a web couple. We start out with the flange couple because we can solve for everything directly. Our moment capacity and our steel component have absolutely nothing to do with A. So solve for that first, and then we back calculate, well, how much capacity do we need out of the web couple in order to safely meet that load demand. Figure out how much steel we need for the web couple, and then just pick a steel pattern based off of those two individual components. So does that make sense? Now, we haven't done that yet, but spoiler alert, we'll be doing that here in a little bit. Now, and then obviously, choose a reinforcement pattern, then verify your assumptions. Okay, this is what we did last time, and I just want to sort of walk through the process and make sure everybody remembers this. So we had a full-blown floor system, and here's what we did. So we started here. We said, okay, oh, that is not what I wanted to do. I wanted to do full screen with not a transparent background. Okay. So we said, here's our floor system. It was 4 KSI concrete, 60 KSI steel. The floor system is 20 foot long. It was subjected to 1 kip per foot dead load, 2 kips per foot live load. Now, one thing to note for your homework assignment coming up, I gave you the load on the beams in terms of kips per foot, but on the homework, it's a pressure load. So you need to distribute that to the beam. So, times the tributary width and all that. So, determine the self-weight of the beam. Remember, when you're determining the self-weight of the beam, you use the tributary width, not the effective flange width, because there is a difference. The tributary width reflects how much the beam is supposed to hold up, the load on the beam. The effective flange width is how much you can count on for strength. So you use the tributary width for load, but you use the effective flange width for resistance. So remember, there's a difference there. Compute MU, and so that can be kind of involved. So ultimately we got 263.0 foot kips, and our next example, I'm just going to give that to you just to skip a lot of this since we've already done that before in previous problems. Next, you say, okay, I compute MN, the required MN, convert that to inch kips, and then figure out if it's a rectangular T-beam, how much reinforcement do you need? So that's our reinforcement ratio. And if we use this much reinforcement, what would our A be? And so our A came out to be about 0.982 inches, and that was far less than the flange height of 4 inches. So this is definitely a rectangular cross section. And if it's a rectangular cross section, AS is rho BD. So AS is like 3.34 square inches. Pick a reinforcement pattern, analyze it. So that's simple. And then you're done. So I don't remember, what was the pattern we came up with? Does anybody remember that from last time? Was it like 3 number 10s or something like that? So, analyze the T-beam, assuming that there's 3 number 10s, compute your efficiency, verify your ACI requirements, and if it works, there's your answer. You use 3 number 10s. It's that simple. All right. So we're going to do this again for a different problem. So here's our new problem. So one of the things with this new problem is I've simplified it for us a bit. So instead of having to determine the effective flange width, I just gave it to you. And instead of determining the factored moment on the beam, I just gave it to you. And I'm not trying to say, it's not me trying to make it easier on you or anything like that. It's just we've done this before. We don't need to do the same thing over and over again. There's a point when it's like, okay, we've done it once, we don't need to do it again. So we have a beam that has 3 KSI concrete and 60 KSI steel. It's being subjected to a factored bending moment of 920 foot kips, and that factored moment includes the beam self-weight. So that is 1.2 dead plus 1.6 live. Everything's factored. All the self-weight and the load combos are already built into that. So step 1 is just MU is 920 foot kips. There's nothing to do. That's kind of the whole point. Now for the beam, I went ahead and gave you that the effective flange width is 54 inches. We have a web width of 15 inches. The flange height is 3 inches, and the effective depth is 24 inches. And like any T-beam problem, all I'm after is this. What is the amount of steel required for this cross-section? That's what I'm after. So I'm going to go ahead and just get right into this. So I'll copy this over so that you have that. So keep in mind, for this problem, we're dealing with an FC prime of 3 KSI and an FY of 60 KSI. Now, if you notice, there's a couple things I didn't give you for this problem. I didn't tell you what the dead load was on the beam. I didn't tell you what the live load was on the beam. I actually didn't tell you how long the beam was. But none of that matters because, the length for instance, the length of the beam. The length of the beam would only be used to determine two things. Your bending moment, which I gave you, and it would also be used to determine the effective flange width, right? Because remember, the effective flange width is the minimum of L/4, your BW plus 16 HF, or your girder spacing. But I gave you that because that's 54 inches. So it's actually not really relevant. Once you get your factored moment, the geometry of the beam actually sort of becomes invalid. So it's kind of an interesting just observation. So step one, compute MU. Well, I gave it to you. MU is 920 foot-tips. Now, you can't get away from doing everything, so we do have to do a couple calcs. Step two is to compute required MN. So that's 920 foot-kips divided by a fee of 0.9. So I guess what I should do over here is to make sure that we recognize that we assumed that. And then remember, we're going to take this quantity and plug it into a row expression. So we're going to be mixing it up with all sorts of inches and KSIs and what have you. So we might as well convert this to inch kips. And so does anybody have a value for this for me?
$122.66.6 repeating.
Okay, so we'll say 12266.7 inch kips. All right, now I have a second on that?
Yep.
Okay. Okay. All right. And I'd argue, I don't care what the beam looks like, that is pretty much going to be your first two steps in any beam design problem. Figuring out what you need to design the beam for and how much it needs to hold up. Now step three, this is where we start making some assumptions whether or not we're dealing with a rectangular T-beam or a true T-beam. So we're going to compute required row value. And in order to do this, we're going to assume a rectangular T-beam. So at this point, this might become a formula that you can just kind of write out. 0.85. Bless you. Hopefully it starts to become a little bit based on memory. 1 minus 0.85 FC prime B D squared 2 MN required. Remember, there's 2 1 minuses. So 0.85. This problem has 3 KSI concrete, not 4. One minus. All right, B is 54 inches and D is 24 inches. Don't forget to square that D on the bottom, and then 2 times 12266.7 inch cubes. So done right, it should be 0 point something. Let's say 5 decimal places just to make sure we all come to the same answer. Remember, row values are tiny, so it's okay to be a little bit precise with this. In fact, if you were to just round to like 3 decimal places, I'd argue that isn't good enough. You have to have some specificity to it. Anybody got an answer for me? Now this one's a big one, so that's okay. Anybody have an answer for me?
0.00202.
202. Do I have a second on that? Okay, you're shaking your head now.
I got 7179.
I think you got outvoted. I got 718 is what I got. Maybe the squared, maybe the that being in inch kips for the 1 minus and then the 1 minus. The only other thing is your parentheses, which that might necessitate doing this like in stages, like maybe do the fraction, and then like the square root of 1 minus that fraction, then 1 minus that, times that fraction. So I know that, what is it, Dr. Wade, he's a big fan of RPN, like reverse notation calculators like HP. This is a perfect formula for that. It's like you start on the inside, work your way out, because it takes less button strokes to do it. So this is a perfect example of where it would be valuable. Okay. I'm going to go ahead and do this on this page, because we got the room. I think we we'll make it. Okay. Now, so what we did here is we computed MU, we computed MN, and then we said, okay, if it's a rectangular beam, this is how much reinforcement we need to safely resist that load. Now what I'm going to do is I'm going to say, let's say we put that much reinforcement in the beam. Let's back calculate our A. Let's back calculate what our stress block depth would be. So back calculate A. Okay? And remember, that's a pretty straightforward formula. It's just rho FYD over 0.85 FC prime. Okay? So 0.00718, we have 60 KSI, and then D was 24 inches, 0.85, 3 KSI. All right, so what are we getting here? $4.05. Do I have a second on that? Okay, so now we're doing this step in order to verify the assumption that this is a rectangular T-beam. In order to verify that assumption, what do I compare that value against? HF. And so what is HF for this beam? 3 inches. So what can you tell me about the assumption that this is a rectangular T-beam? That assumption is false, because the stress block is deeper than the flange, then the top flange. So, assumption is invalid. A is greater than HF, which means we have a true T-beam. Now, does that make sense that the assumption was invalid? Is everybody okay with that? Is everybody okay with the understanding that we're dealing with a true T-beam and not a rectangular one? Well, I hear. All right, so if that's the case, we don't go to step 5, we don't go to step 6 or step 7. We just immediately, skip collecting $200 and go straight to step 8, okay? Because step 5, 6, and 7 are for if that assumption is true, and step 8 and on is if that assumption is not true. So what we're going to do is going to skip those 3 steps and go straight to step 8. Does everybody have this? Do I need to go back? So we're going to say go to step 8. Okay? Now, the way that step 8 works is we start off by looking at the flange, we'll call it the flange steel couple. Okay. Now, what we do here in this step is we recognize the following. Okay, and I'm going to just put this on the board because it doesn't really matter for our calc. So you can copy this down if you want, but you don't have to. So when you're looking at this couple, the compressive force in the flange is 0.85 FC prime times the area of the flange, right? And then that has to be counteracted. If that's a compressive force, there has to be some tensile force that counteracts that. And that tensile force is going to be whatever steel we need, whatever steel we need times Fy, right? And then our moment capacity is just going to be one of these forces, so CF or TF, doesn't really matter which one, times the moment arm, D minus HF over 2, okay? So what we're going to do here is we're going to solve for 2 quantities. We're going to solve for this, right? And we're going to solve for this, okay? Because they're the 2 quantities that right now we don't know. Look at this, look at these expressions. What do we know? I'm getting steel design mixed up. That's a lowercase step. All right, what do I know looking at our beam? I know FC prime and Fy. I know B, that's 54 inches. B sub W, what was that? That was like, was it 12 inches? What was that? 15. Okay, so this is 15 inches. That's 3 inches. I know that. This term and this term are really the 2 things I don't know right now. Okay? Now, how do I solve for this one? How do I solve for that? All I do is I set C equals T. So 0.85 FC prime B minus BW times HF equals the area times Fy. And if I'm solving for that, just divide all this by Fy, right? That's all I'm doing here. So I don't want you to think, the point of me doing that is when I say, okay, here's the formula for ASF, and it's 0.85 FC prime B minus BW times HF all over Fy. I don't want you to think, where in the heck did you come up with that formula? Did I just, like pull it out of thin air, break out the crystal ball and just say, okay, that's the answer? No, it's just basic, C equals T, okay? And then, so we got fractions, 0.85, 3 KSI. I believe that was what, 54 inches? Did I get that right?
Yes.
Okay. All right, so ASF equals put this over here. whatever we get. Anybody have an answer for me? We'll say just like 2 decimal places. I don't think you need to get super intense with this. 4.97. Do I have a second on that? Okay. All right. And then last, we'll do MNF. So that's just going to be, again, C or T times that moment arm. Now, C or T, which one do you want to use?
T.
T. I'm lazy, so let's just do the one that has the least amount of terms. So, ASF, FY, D minus HF over 2. So, 4.97 square inches, 60 KSI, and then 24 inches minus 3 over 2. And let's go ahead and leave that in inch tips, okay? Anybody got an answer for me?
6709.5 inch tips.
Do I have a second on that? All right. Okay. All right. So now we go on to step 9. So if step 8, I'm calling that the flange steel couple. Step 9, we'll call that the web steel couple. Okay? And again, the formula that I'm using is not very, very magical. So what am I doing here? This is what I'm doing. Okay? So our nominal capacity is our nominal capacity of the flange couple plus the nominal capacity of the web couple, right? So factor everything. Right? Phi MN's got to be greater than or equal to MU, right? So set this term here, set this term equal to MU, and just solve for what we want, which is that. So bring that over, divide by phi, that's all I'm doing, okay? So when I write this formula out, I don't want you to, again, I don't want you to think that this is magic. It's really not, okay? So here's the formula. So MNW is MU minus phi MNF over phi. Again, all there is to it. Now, MNF, we said was 6709.5 inch kips. What was MU? Remind me. Well, that was from way back at the very beginning of the problem.
920.
Say again?
920.
920 what?
Foot kips.
There we go. See a problem? So, what should we do? Well, we have an option. We can either convert this to foot kips or convert this to inch kips. Since we're in design mode, I think what you ought to do whenever you're in the design phase is pick a unit system and stick with it. And since your beam dimensions are in inches and your FC primes and your FYs are in KSI, convert that to inch kips. So take that MU, convert it into inch kips. So what's 920 times 12?
11,040.
11040. So 11040 inch kips minus 0.9 times 6709.5 inch kips over 0.9. And so MNW equals what? They got an answer for me?
5,557.17. That's good.
Do I have a second on that? Okay, good. Okay. All right. So, is everybody sort of following what we're doing? We took the T-beam, because it's a true T-beam, and we split it up into a rectangle, or the flange web couple, the flange web couple, and the flange steel couple and the web steel couple. The flange steel couple and the web steel couple. The reason that we're doing that is because for each of those couples, what we want to do is we want to determine the required area of steel. So for the flange steel couple, we determined that we needed 4.97 square inches of steel. Now what I want to do is I want to try and determine how much steel we need for the web steel couple. Now I know I need this much capacity out of the web steel couple, so this, I don't want to say it's the last step because it's not, but I'd say it's the last rigorous step in our design is to compute ASW. And the way that we do that is we recognize that the web steel couple is a known cross-section. We know how wide the web is, we know the depth, we just don't know the steel. So all I'm going to do is use my same expression for rho that I have been using all along. Tweaked just a tad. So we'll call this rho W equals the following. Now, if you look at this formula, this is the same formula we've been using for a while with a couple adjustments. Instead of just the MN for the whole section, it's MN for the web steel couple. And then because we're looking at the web steel couple, we're not looking at the entire effective flange width, we use BW, the width of the web. So that's the only thing that's different. Other than that, it's the same formula. I'll give you all a second on this. Again, just the BW is 15 inches, not the full 54, and just use that for your MN. Other than that, same expression. We can set up 2 decimal places. I don't think it needs to be much more explicit than that.
I got 4.53.
4.53. Do I have a second on
I
that?
think it's a little large.
A little large.
That's the news. Oh,
What?
oh, my bad.
You missed.
I might have done it.
I don't think you did. I got
I thought
4.53.
the row was kind
You're
of
good. I thought we were doing a road.
Yeah, you skipped.
Oh, I skipped a step. You're right, I did skip a step. Sorry. So that's that's ASW. What's row? Sorry. I got something like here. How about this? Is that what you got?
Yeah.
Right here. I'll put that over here. 0.01257. That's what I got here. And then ASW. Okay. ASW
Yeah, when you
is
said the 2 decimal places, I was like, what?
yeah. Yeah, I skipped a step. And then, sorry, it's row BD, but the B is BW. So 0.01257 times 15 inches times 24 inches. Now this, did you get 4.53? Sorry. Did everybody get this? Okay, sorry about that. Sorry about that. Okay, so this term right here is 4.53. Okay? All right. Now we know what we need to design for, okay? We took this true T-beam and we split it up into 2 couples, the flange steel couple and the web steel couple. When we were dealing with the flange steel couple, our math determined we needed this much steel. And for the web steel couple, we determined we needed this much steel. So for designing the beam, what we're going to say is we need to provide that much steel. Just add it up. And we pick our steel pattern based off of that. Okay? So I'm going to sort of walk you through the very, very end of this problem. So step 11 is to select your reinforcement for maybe our trial design. So ASF is 4.97 square inches. ASW is 4.53 square inches. AS required is 9.50. Just add them up. Now that's a lot of steel. Like that's a lot, okay? But this beam's got a lot of moment on it. I mean, it's got 920 foot kips a moment. That's a lot of load. So it sort of fits. Here is what I did for my design for this problem. So I'll just show you. So here's the T-beam. This dimension is 54 inches. This dimension is 3 inches. This dimension is what, 24 inches. And this dimension is, what is that? Is that 15? 15 inches. What I did for my design is this, okay? Can anybody remind me, what is the area of a number 9? 1 square inch, right? So if you put 10 number 9s in this, it would fit, or it would meet the area requirements. But 10 number 9s in a single layer will not fit within 15 inches. So what I did is I said, let's do 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So when I look up my width requirement, my beam width requirement, I don't look up the width requirement for 10 bars, I look it up for 5, right? And if you go to your beam design aid, say note, so that D distance goes to, the center of that steel. Say note, for 5 number 9s, the beam minimum is 14.28 inches. And then your very, very last step is to verify your trial design. Now, what I'm not going to do is do that for you right now. You all have all of the skills necessary to do this on your own. So here's what I will tell you at the end what happens. So remind me, what was MU? It was 920? Is that what it was?
Yeah.
920 foot kits. You all should be able to take that beam that's right there and compute FEMN. If you do that, you will find that FEMN is 935.5. Is that a good design? Is that a safe design? Yes, because the capacity, the FEMN, is greater than the MU. In fact, the efficiency is 98.3%. And for this design, the strain is greater than the limiting strain, which verifies that phi equals 0.9, and your area of steel is greater than AS min. So that design does work. My advice for you is to do that on your own to make sure that you know it works. But that's the answer. So the problem, this problem, we're supposed to design, select that reinforcement. That's your reinforcement. Sound good? All right, it is 10:47. We're not going to have enough time to get into our next topic. So I'm going to close it for today, but I am going to very, very briefly introduce it. Our next topic, and this is actually our final topic for moment capacity, because afterwards we're done with moment, is a doubly reinforced section. After moment, we look at a completely different design procedure, and that's designing for shear, because we haven't talked about shear yet. That is our next topic. But our last topic in moment is a doubly reinforced section, and so a doubly reinforced section, what you have is you have a beam like this. There's no such thing as like a triply reinforced or a quadruply reinforced. That's not what we're talking about here. A singly reinforced section only has steel in the tensile region. But a doubly reinforced section has steel in the tensile region and in the compressive region. Now, there's a couple reasons why you would put steel in the compressive region. First off, the steel tends to already be there anyways. When you tie together your, what we call the rebar cage for your beam, you tend to put some steel up top just to tie everything together anyways, okay? So that would be the first reason to consider it. The second reason, you do get a little bit of a bump in capacity, like you're putting steel up top. Steel is a material that is stronger than concrete, so by accounting for it, you do get a little bit of a bump in capacity. But there are also some other reasons. It doesn't really make sense now, but it will later. When you put steel in the compressive region, you get some benefits on your long-term deflection performance. After shear, we'll talk about deflections. And so deflections will probably be a post-spring break topic. But we'll see how rho prime, the reinforcement ratio for your compression steel, shows up a little bit later. What makes a doubly reinforced beam complicated, and we'll talk about this later, but what makes it complicated is ACI requires that the tensile steel yields, but the compressive steel doesn't have to. The compressive steel could yield, it could not. And if it doesn't yield, it makes the analysis a bit trickier, okay? It gets a little quadratic, gets a little intricate. It's not hard, but it's a little longer. We'll talk about that next time. That's all I got. I will see you all in a couple minutes or on Wednesday.